F650 Interactive Learning course. In this course, we will first review some of the basics of protective relaying before proceeding on to the F650's installation, wiring, and configuration. Introduction to the power system. Modern electrical power systems are remarkably dependable, delivering energy 24 hours a day, 365 days a year without any interruption. Protective relays have an important part in ensuring this continuous service. The protective relay is always ready to react instantly to protect the system from damage and to minimize any service interruption. To better understand how protective relays fit into the modern power system, we will first review the makeup of the system. A power system is designed to generate electric power of sufficient quantity to meet present needs and estimated future demand of the users in some particular area, to transmit the power to the area where it will be used, and then to distribute the power within the area. For normal operation, these are the minimum requirements. Let's take a closer look at the key components of a power system. Power system components. There are many sources of electrical power: gas, nuclear, hydroelectric, and alternative. The electrical power that is generated by these sources must equal the power that is consumed. Let's take a look at a simple system consisting of a generator, steam turbine, prime mover and control system, and a residential load. As stated, the generated power must equal the demand, which is constantly changing. As the load increases, the generators would tend to slow down, resulting in a reduction of output voltage and frequency. The generator's control system will sense this and input more mechanical energy to match the increased load. If the demand decreases, the generator will speed up. The control system senses this and then takes appropriate action to reduce the mechanical energy input into the system. Once generated, the voltage is fed to step-up transformers for transmission to reduce the I²R losses, and then at the substation it is stepped down for distribution. Given that the power loss during transmission is equal to the current squared flowing through the transmission line times the resistance of the transmission line, the step-up transformer increases the voltage level, thereby reducing the current, resulting in an overall reduction of power loss during transmission. The Institute of Electrical and Electronics Engineers, sometimes referred to as the IEEE, have divided voltage systems into low, medium, high voltage, and extra high classes. Low voltage systems are below 1,000 volts. Medium voltage systems are between 1,000 and 100,000 volts. High voltage systems are between 100,000 and 230,000 volts, and extra high voltage systems are considered to be any system above 230,000 volts. The voltage levels may vary in different parts of the world, but the names of the classes, for the most part, remain consistent. The three-phase power travels from the generating station over high power lines to substations. Different voltages are required for residential, commercial, and industrial customers. And so, at substations, breakers and transformers route and step down the voltage to a suitable level for distribution. From the substation, the industrial or commercial power lines take the power above or below ground to a large transformer which steps the three-phase voltage down to a suitable level for the plant or building. For larger commercial or industrial users, this voltage may be in the medium voltage range. In this case, there will be an additional substation on site. The power would then be routed from the transformer or transformers via medium or low voltage switchgear to different areas of the plant or building for further distribution via switchboards and panel boards. The power system can be thought of as a chain, the links of which are the generators, the power transformers, the switchgear, the transmission lines, the distribution circuits, and the loads. The arrangement of these links are as shown. The failure of any link destroys the capacity of the chain to do the work for which it was intended. One way in which the continuity of the chain can be preserved is to provide alternate links. For example, the transmission lines, being exposed to the natural elements, are more vulnerable to short-circuit faults than the power transformers and switchgear. Hence, alternate transmission lines may be economically justified, whereas alternates for the power transformers and switchgear would not. The network of power systems now blanketing many countries are often interconnected at many points to accomplish this. Since each link in the chain involves a large investment in equipment, alternates are frequently prohibitively expensive. To ensure both maximum return on the investment and to provide reliable service to satisfy customers, the whole power system should be kept in operation. This is accomplished in two ways. The first is by the specification of the design and the maintenance of each component of the power system to prevent a failure which would affect the component's usefulness in the power system. The economic considerations of design and maintenance procedures will allow this to proceed only so far. The second procedure which is followed is to control and minimize the effects of any failures that do occur. This is where the protective relay fits into the power system. The protective relay is the device which operates to disconnect a faulty part of the power system, thereby protecting that part and the remainder of the system from damage. The function of protective relays. Protective relays are placed on the system to reduce the number of alternate links to a minimum. They do so by avoiding equipment damage or by limiting it to the single component that may be in trouble. The relays quickly locate the fault and trip circuit breakers which will interrupt the flow of current into the defective component, thereby isolating. Two benefits of this quick isolation are, first, it minimizes or prevents damage to the faulted component, thus reducing the time and expense of repairs, and permits quicker restoration into service. The second benefit is that the quick response minimizes the seriousness and duration of the fault's interference with normal operation of the unfaulted parts of the system, allowing them to continue to supply their normal power. In many cases, the unfaulted parts of the power system can supply the additional power to replace what was normally supplied through the faulted component. The protective relay uses current and voltage instrument transformers to acquire information about the system, such that a fault can be located. The type and location of the instrument transformers, the circuit breaker which is to be tripped by the protective relay when it operates, and the signal level required to operate the relay is selected when the relay is applied to the power system. The function of protective relaying is to immediately remove any component of a power system when it suffers a fault that might result in damage to property or present any unsafe conditions. In addition, protective relays can provide information on the locations and types of failures that occur. This information not only helps with equipment repair, but also provides the means for analyzing the effectiveness of the protection scheme. We should note that protective relays are not always part of a protection scheme. Fusing, reclosers, and sectionalizers are employed in some cases to keep costs down. Circuit breakers are located between each power system component, which makes it possible to isolate and disconnect the faulty component. If a breaker isn't installed between two adjacent components, both components will need to be disconnected for a failure in either one. One of the protection engineer's most powerful tools is the concept of zones of protection. A protective zone is an imaginary boundary around each major power system component. The boundary of a protective zone represents the region that a particular protective element covers. It is necessary for these zones to overlap to ensure proper protection. If two zones did not overlap and a fault occurred at the boundaries of these zones, it is possible that no relays would be tripped. For failures within the overlap area, more breakers will be tripped than needed to disconnect the faulty element. However, the overlap areas are relatively small, and the probability of failure in this region is very low. Therefore, the tripping of too many breakers for a fault in the overlap area will be infrequent. The preferred practice is that adjacent protective zones overlap around the circuit breaker, so that for failures anywhere other than in the region of overlap, the minimum number of circuit breakers will be tripped. If the zones of protection are set up such that overlap occurs on only one side of the breaker, the relaying equipment of the zone that overlaps the breaker must also be able to trip the breakers in the neighboring zone in order to completely disconnect faults in certain areas. This can be illustrated in the following example. For a fault located as shown, the circuit breakers of Zone B will trip, but because the fault is outside of Zone A, the relaying equipment of Zone B will need to send a trip signal to the breaker in Zone A. A potential drawback of this is that the breaker in Zone A will be tripped unnecessarily for faults occurring in Zone B to the right of breaker C. Circuit breakers. Circuit breakers are an essential part of any protection scheme. At least one or more circuit breakers, in conjunction with the relaying equipment, are required to isolate a faulted power system component. A circuit breaker is defined as a mechanical switching device capable of making, carrying, and breaking currents under normal or abnormal circuit conditions such as those of a short circuit. CT placement with circuit breakers. The term dead tank design, when applied to breakers, means the contact enclosure is insulated from the contacts. The dead tank design typically incorporates CTs in the bushing pocket of the tank on both sides of the contacts. As indicated earlier, the protective zones should overlap to ensure that no section of the power system is left unprotected. This overlap is conveniently achieved by the placement of CTs and their connection to relays as shown. With the live tank CB design, the contact enclosures are at the same potential as that of contacts, eliminating the need for insulation between them. It is, however, not possible to incorporate CTs within the bushings, as the entire CB is at line potential. In this case, the CTs have to be mounted to a separate freestanding structure, and only CTs with multiple secondary are employed. In general, the most common faults that occur on a power system are short circuits. We will now consider relays that are dedicated to protection against short circuits. There are two groups. The first group is called primary relays and is the first line of defense, while the second is called backup relays and functions only when the primary relaying fails. Backup relaying can be classified as either local or remote. Faster reacting backup relaying can be achieved by using local backup relaying systems. This means that the relay providing the backup is located on the same component that is being protected by the primary relay. Local backup protection is often used to protect against failure of both the primary relaying system and the associated circuit breaker. The only potential drawback is that local backup relaying often uses the same CTs, VTs, circuit breakers, etc., which can fail, likely resulting in failure of both the primary and local backup relay. Duplicate systems. On high-voltage systems, it is a common practice to duplicate the protection systems to ensure proper operation if a failure occurs. In some cases, only the relays are duplicated, while in other cases, the entire protection system is duplicated. This is the preferred choice when economically justifiable. Let's take a look at several backup strategies being used within one power system transmission line. Here we see that relays R1 through R6 are the primary relaying. The D group of relays is the duplicate system, and the L group of relays is the local backup relaying. When a fault occurs at location F, relays R1 and R2 are the primary relays that are programmed to identify and clear the fault. The fault at location F is within R2's zone of protection. Let's assume that when the fault occurs, R2 fails to operate. The duplicate relay D2 should have operated at the same time. However, let's assume that relay D2 of the duplicate system has also failed. The local backup relay L2 should now operate a short time after the primary and duplicate relays due to its coordination with them. If all three fail, the backup function of relays R3 through R6 is to provide remote backup to R2, D2, and L2. Let's look at an example of a breaker failure protective element. In this example, the protective relays operate correctly, but the associated circuit breaker fails to clear the fault because of some malfunction within the breaker or its control circuits. The fault will now remain on the system until some other means is used to clear it. In our example, the primary or backup relays start a timer once a fault has been detected. The timer will then time out and send a trip signal to all breakers that can feed the failed breaker with power. Until the early 80s, almost all protective relays in use were based on an electromechanical principle of operation. Their designs were limited in configuration, and most supported only one protective element, resulting in a requirement for many expensive electromechanical relays for a protective solution. This, coupled with the expense of periodic calibration, translated into high initial cost for an electromechanical relaying solution, in addition to high maintenance costs associated with the mandatory periodic calibration of each electromechanical relay within the system. In electromechanical relays, a moving part like a disc or a plunger is placed in a magnetic field produced by the input signals, known as actuating signals or measured quantity. The disc or the plunger moves and touches a contact when the intensity of the magnetic field exceeds a preset limit. Electromechanical relays fall into one of four styles or categories depending on the type of moving part. These are the plunger, the hinged armature, the induction disc, and the induction cup. The plunger and hinged armature operate under the principle of magnetic attraction. The armature is attracted into a coil or to the pole face of an electromagnet. This principle works with either alternating or direct current measured quantities. The induction disc and induction cup work under the principle of magnetic induction. Torque is developed in a movable rotor in the same way that it is produced in an induction motor, which means that they can only be used with alternating current measured quantities. Now let's quickly review the theory of operation of each style of electromechanical relay. The plunger style of construction consists of a bar or cylinder armature which is attracted axially into a solenoid coil. The armature carries the moving portion of the contact, which meets a fixed contact once the current magnitude of the measured quantity exceeded a preset amount. The hinged armature construction, which also includes the cantilever and beam type of construction, consists of a flat plate or bar type of armature, which pivots at a fixed point when attracted to the pole face of an electromagnet. The armature carries the moving portion of the contact, which meets a fixed contact when the armature is picked up. An advantage of the plunger and hinged armature style of construction is that they have no inherent time delay, hence they are used for functions which require instantaneous operation. As the hinged armature relays operate, the length of the magnetic air gap changes, resulting in a slightly greater force required to just pick up the armature than the amount of force that is required to release the armature. This translates into a difference in the amount of measured quantities for pickup and dropout, which is a slight impairment for this style of relay. This shortcoming also applies to the plunger style of construction, but to a lesser extent. The induction disc element consists of a metallic disc of copper or aluminum, which rotates between the pole faces of an electromagnet. There are two styles of induction disc, the shaded pole style and the watt-metric style, each having its own principles of operation. In the shaded pole style, a portion of the electromagnet pole face is short-circuited by a copper ring or coil, which causes the flux in the shaded section to lag the flux in the unshaded section. Once the measured quantity exceeds a preset level, the induced torque on the disc will cause it to rotate, resulting in contact closure. A spring on the disc allows the contacts to open once the measured quantity falls below a preset level. The watt-metric style uses one set of coils above the disc and another set of coils below the disc. In either case, the moving contact is carried on the rotating shaft of the disc element. The induction disc style of relay is always used as a time delay element because of the inertia of the moving disc. The time delay feature is added by means of a permanent magnet. The disc rotating between the poles of this magnet causes an induction drag. The induction cup element consists of a metallic cylinder with one end closed like a cup. The cup rotates in an annular air gap between the pole faces of electromagnets and a central core. The induction cup unit uses 4 or 8 poles spaced symmetrically about the circumference of the cup. Due to the low inertia of the rotating parts of the relay, this style is capable of high-speed operation. Hence, it is used for functions requiring instantaneous operation. The multiplicity of poles also permits measurement of more than one electrical quantity. In the 1970s, many relay manufacturers introduced electronic relays, which simply emulated their electromechanical predecessors, and in many cases, the design still required costly periodic calibration. In the early 80s, the microprocessor-based relay or digital relay was introduced. Standard features such as multiple element support, low maintenance, built-in high-speed communication, waveform, event log, improved element performance, and built-in programmable logic controller functionality has enabled the digital relay to revalorize the protection industry. Let's take a closer look at the operation of a modern microprocessor-based relay. Through the use of current and voltage transformers, the relay receives information about the power system. These quantities are converted into symmetrical components and passed on to the active protective elements within the relay. The protective element or elements within the relay initiates the appropriate action based on these quantities and the configuration settings within the relay. These elements may work independently or through the use of logic gates. The type and number of protective elements within a particular relay will depend upon the type of protective application the relay has been designed for. For example, a relay designed to protect a transformer will have some protective elements not found in a relay designed to protect a feeder, and vice versa. Instrument transformers supply protective relays with current and voltage for measurement. This high current and voltage is first converted by the transformers to much lower quantities that can safely be injected into the relay for measurement. It is important to note that the proper selection of current and voltage transformers for protective relaying applications is the responsibility of the system engineer. CT's Introduction. The function of a current transformer, or CT, is to take a current flowing through a wire or cable and step it down to a magnitude that a protective relay can measure. A primary characteristic of CTs is their conversion ratio. In this example, our conversion ratio is 100:5, meaning that if 100 amps are passed through the primary phase wire, the CT will scale this down to 5 amps and direct it to the relay via the secondary windings. The 5 amp measure is known as the secondary nominal current. If a fault were to occur on this phase that increases the primary current to 200 amps, then 10 amps would be passed to the relay through the secondary windings consistent with the ratio. CTs have two main secondary ratings, 5 amps and 1 amp, while primary ratings are available at various different levels, for example 100, 150, 200, etc. Types of CTs. A common current transformer construction is one in which the power system phase wire is passed through the hole in the center of an annular core or ring, which is called a window. This forms the primary winding. A second insulated wire is then wound around the core and then brought to the relay for measurement. This is known as the secondary winding. A CT with this type of construction is typically referred to as a toroidal or donut style of CT. CT selection. Proper protection starts with the selection of current transformers. The following is a simple procedure that can be used to check whether or not there is the possibility of CT saturation. This procedure is as follows. The first step is to ensure that the primary rating of the current transformers is equal to or greater than the expected full load current. We can determine the primary rating of a CT by looking at its ratio. For a ratio of 100:5, a CT has a primary rating of 100. Meaning that no more than 100 amps should be passed through the CT under normal operating conditions. The second step is to ensure that the CT can drive what is called the attached burden at the worst-case fault current levels without saturating. The burden refers to the total load resistance of the secondary circuit. The calculation for the burden is CT secondary resistance, which is the amount of resistance on the secondary windings on the CT, added to the connection wire resistance, which is supplied by the manufacturer, added to the relay's burden resistance, which is the resistance within the protection relay. As explained in the previous section, a CT becomes saturated when the voltage secondaries reach the knee point of the excitation curve. To determine whether the CT can drive the attached burden under worst-case fault conditions without saturating, we must determine what the CT's secondary voltage will be at the time of this fault. The CT secondary voltage at the time of fault is equal to the burden resistance times the maximum fault current divided by the CT conversion ratio. The resulting value is then plotted onto the CT excitation curve. If the value plotted on the curve is below the knee point, then the CT will not saturate under these worst-case fault conditions. If the value is equal to or greater than the knee point, then the CT will saturate. Now we will look at a practical example to help us further explain this calculation. Let's assume that we have a motor that draws a maximum full load current of 285 amps. The first step is to choose the appropriate CT. It is customary to select a CT that has a primary rating falling between 50 to 100% of our maximum full load current, in this case 285 amps. Possible CTs for this use would be 300 to 5, 400 to 5, and 500 to 5 CTs, because the primary rating falls between 50 to 100%. In this case, we would select the CT that would fall the closest to 100%. The reason for this is the higher the CT ratio is over the full load current, the less sensitive that CT will be. Since accuracy is always imperative, we will select a CT with a 300 to 5 amp conversion where the primary rating is 300 and closest to the 100% primary rating. The next step is to ensure this CT doesn't saturate under worst-case fault conditions. If it does, a higher ratio CT, such as the 400 to 5 CT, may need to be chosen. The first step in determining whether a CT will saturate is calculating the maximum voltage that will appear on the primary of the CT under a worst-case fault condition. The maximum fault current at the load is determined by a fault study, and in this case was determined to be 6,000 amps. Next, we will calculate the secondary resistance, or burden, using the stats provided. The phase CT's secondary resistance, that is, the resistance of the windings on the CT, is equal to 0.088 ohms. The length of each wire from the CT to the relay is 50 meters and has a rated resistance of 2.5 ohms per kilometer. The total burden is equal to the CT secondary resistance, which is 0.088, plus 2 times the lead length of 50 meters, multiplied by the lead resistance of 2.5 ohms per kilometer, and then divided by 1,000 meters. This is then added to the relay burden of 0.008 ohms, resulting in a total burden of 0.346 ohms. Now the secondary voltage at the time of a worst-case fault can be calculated. First, the total burden resistance, 0.346 ohms, is multiplied by the maximum fault current, 6,000 amps. The result is then divided by the CT ratio, 300 to 5. Concluding that the secondary voltage at the time of a worst-case fault is 34.6 volts. With the maximum secondary CT fault voltage calculated, the final step is to refer to the CT excitation curve. By plotting the 34.6 volts value on the excitation curve, we notice that it falls well below the knee point, indicating that it will not saturate under a worst-case fault condition. If the factors affecting the burden were ever to change, or a higher fault current is measured, these calculations must be repeated to ensure the CT does not saturate. Potential transformers. The next type of transformer we will cover is the potential transformer, symbolized as PT, or sometimes known as voltage transformers, symbolized as VT. Similar to current transformers, potential transformers scale down the voltage passed through them, as opposed to the previously mentioned current. The scaled-down voltage is then routed to a protective relay for measurement. Also as in current, a PT is classified with a conversion ratio indicating the amount the primary voltage is scaled down. For example, 60 to 1 scales a 7200 kilovolt primary voltage down to 120 volts. There are 2 different types of potential transformers used today: the electromagnetic voltage transformer and the capacitive voltage transformer. Electromagnetic voltage transformers are usually used when accurate metering needs to be performed for lower voltage applications. Capacitive voltage transformers are commonly used in high voltage transmission line applications where the voltage is higher than 66 kilovolts. Electromagnetic voltage transformers have dense winding drops designed to accurately scale down the voltage and make sure the ratio is consistent for all variations in the input voltage. Due to the small amount of voltage drops per winding, the electromagnetic voltage transformers will increase in size as the rated primary voltage also increases. Likewise, the cost of electromagnetic voltage transformers tends to increase at a disproportionate rate to the primary voltage rating. Capacitive voltage transformers, or CVTs, are normally used on higher voltage applications. The CVT is basically a capacitance potential divider and consists of the following components: coupling capacitors, typically 10, compensating reactor, step-down transformer, and a ferroresonance suppression circuit that is found just before the output terminals for connecting to a relay. The accuracy of a PT's operation is specified in the displayed label format. The first item in the label indicates the accuracy class of the PT. The three common accuracy classes are 1.2, indicating PT accuracy between 98.8 and 101.2%, 0.6, indicating PT accuracy between 99.4 and 100.6%, and 0.3, indicating PT accuracy between 99.7 and 100.3%. The next character in the label is a letter designating the burden rating. The typical burden designations and their corresponding ratings are as follows. The W rating indicates the PT will operate accurately as long as the burden doesn't exceed 12.5 volt amperes. The X rating indicates the PT will operate accurately as long as the burden doesn't exceed 25 volt amperes. The Y rating indicates the PT will operate accurately as long as the burden doesn't exceed 75 volt amperes. The Z rating indicates the PT will operate accurately as long as the burden doesn't exceed 200 volt amperes. And the double Z rating indicates the PT will operate accurately as long as the burden doesn't exceed 400 volt amperes. If at any time the burden exceeds the PT's rating, the accuracy classification will be compromised. In this example, the PT rated 0.6 double Z would have an accuracy between 99.4 to 100.6% as long as the burden of the PT remains under 400 volt amperes. Feeder protection is a broad term that refers to sub-transmission lines and distribution circuit protection. Sub-transmission lines refers to lower voltage transmission lines that connect the transmission system to the distribution system. Distribution circuits connect the sub-transmission system to the utilization apparatus. The issues surrounding sub-transmission and distribution system protection are very similar. In most cases, instantaneous and time-over-current protective elements, in addition to directional elements, are the most economical approach for both phase and ground fault protection. In this next section, we will take a look at the most common protective elements, which are the overcurrent elements. We will be studying their operating characteristic curves and how they are applied to the protection of distribution circuits. Modern microprocessor-based protective relays support many different protective elements. These elements may require one or two power system quantities, such as current or voltage. If only one measured quantity is used, the protective element will respond to the measured quantity over time. If the protective element uses two quantities, such as both current and voltage, the element may respond to the phase angle between the two quantities, the magnitudes of the two quantities, or to a combination of magnitude and phase angle. In protective relaying, it is common to use an operating characteristic to show the relationship between the quantities that will cause the relay to operate. As stated earlier, if only one measured quantity is used, the protective element will respond to the measured quantity over time. The operating characteristic will take the form of a graph, with the measured power system quantity plotted on the x-axis against time on the y-axis. The graph, or operating characteristic curve, clearly demonstrates the boundaries between three regions. The first is the none-operate region, and as the name implies, the element will not operate when the intersection of the two measured quantities falls within this area. The second is the curve, which represents the point at which the element picks up. The third region is the operate region. The element will operate when the intersection of the two measured quantities falls within this area. Operating characteristic curves are useful for determining the relay settings that will provide the necessary speed, selectivity, and sensitivity to protect the power system and to coordinate with other protective devices. It is common for the curve to be drawn such that it does not extend to either axis. When the curve is drawn like this, it is implied that for every value of x beyond the curve, the value of y will remain the same. A very common requirement is to remove a component if the amount of current flowing into the component exceeds certain levels over certain amounts of time. The time and instantaneous overcurrent elements were created for this purpose. The instantaneous overcurrent protective element operates once the current has exceeded a pre-programmed level. If electromechanical relays are used, the relay will require some short time to operate. Where it is desired to have more time delay before operating, the time over current protective element is used. The trip time varies inversely with current. The element will typically support several characteristic curves. The three characteristic curves most commonly used are called inverse, very inverse, and extremely inverse. They are said to be a family of curves. In other parts of the world, different sets of curves are used, and some, like the GE digital energy relays, allow you to create your own curves. During the selection of the curve, the protection engineer will be able to use a time multiplier to effectively shift the curve up or down on the time axis, in addition to a scaling adjustment to normalize the curve to the desired pickup level. That is to say that the pickup will be equivalent to 1 per unit, or 100% on the x-axis. The setting of a series of coordinated time-over-current relays on a feeder or distribution circuit begins at the point farthest removed from the generating source. As the relaying is set and coordinated back toward the generating sources, the time required to clear a fault becomes longer as the source is approached. Under certain fault conditions, this could be a disadvantage, and so instantaneous overcurrent elements are used in conjunction with the time overcurrent elements to provide high-speed primary protection. These elements must be set to pick up under maximum fault current conditions for three-phase faults somewhat short of the end of the line. The shaded area of the figure illustrates the improvement in tripping time obtained with instantaneous elements. Ground relaying of sub-transmission and distribution circuits is accomplished by means of instantaneous, time-over-current, and directional overcurrent elements. These elements can generally be made to operate faster and with more sensitivity for ground faults, and still maintain selectivity because their connections render them immune to load currents. The directional element requires a source of polarization that is obtained either from a current transformer in the neutral of a power or grounding transformer, or from the broken delta of a grounded neutral Y-delta potential transformer bank. This concludes the theory portion of the F650 CD. You should now have the understanding necessary to continue with the study of F650 relays. More in-depth study of feeder theory, along with other forms of protective relaying theory, can be found on the GE Digital Energy Fundaments of Modern Protective Relaying Interactive Learning CD.